All right, good morning, everybody. We'll wait a few more minutes. It looks like there's still people coming in. Wow. I hope yesterday was useful to people. I know that there was some overlap with what we talked about in the science assemblies, but I didn't. Not everybody made it to the science assembly, and I did try to make it a little bit different. Good morning to those of you just joining us. Um, I'm just gonna wait a few minutes for people to finish trickling in. Well, I don't want to wait too long because actually this first part of today is kind of super packed. So, um, unfortunately, the content and the time span for that it turned out weren't as great a match as I thought. So let's get going. Good morning and welcome again to the SEOC workshop page, day two. Um, this is your SEOC and all of their members, and we on the from LSST, we really appreciate all of the work the SEOC do. Today, we're going to talk about more details of some of the things we talked about yesterday. Code of conduct reminder, please be kind. We're here to help make Ruben the most awesome thing it can be together. So let's be kind, be honest, be inclusive. If you do have a problem, please reach out to me or Federica Bianco or your science collaboration point of contact. Okay, quick review what we did yesterday. We went through the current OPSIMs and we talked about metrics, primarily in sort of a high level over the whole survey kind of point of view. And today we'll talk about some particular aspects of those simulations and what we're actually seeing from data management and from various aspects. And at the end of today, we have the a time to talk more specifically about DESI. So that we will cover that today. And David, I see you're here. I wasn't able to make sure we had the right time, but I think you're up for talking about DESI in that last section a little bit, right?
I'm here all day. Yep.
Perfect. Thank you. All right. Right. And on Monday, we have this session to get feedback from the science collaborations. So we can adjust these times as needed for what people's feedback wants to be. All right. So today, the first thing up is details of the FBS configuration and what we're starting the survey with. So this is the chunk of today that is quite dense, and it's hard to talk about the FBS and how it's doing what it's doing in a way that makes sense to people without actually telling you a little bit about what's going on inside the FBS. So that's what I'm going to do. And if you have absolutely no interest in the inner workings of the FBS, this might not be for you, but I actually think it's pretty fascinating. So hopefully it'll be interesting to you too. Some of this might be a little bit fast going through because, like I said, we made the agenda before we figured out exactly what had to go in this pot. And but I'm gonna try for that. Anyway, here we go. Light introduction to the inside of the FBS and what that means for the start of the survey with V5.3. So inside the FBS, what we have is the whole scheduler configuration. And inside the FBS, there is a list of lists of surveys. The list is what we call tiers. So it's like you can think of it as prioritizing. A higher tier always has priority over a lower tier. So if we put deep drilling over a tier with lots of pairs, if the deep drilling survey can request an observation, it will. Within a tier, those surveys compete. So if you have multiple surveys inside a tier, they can compete with each other to say, oh, I really want this observation, or somebody else say, I kind of want this one, but they'll go head to head to see which survey is going to choose the observation for the upcoming observation to be taken. So this is important to keep in mind. We have this concept of tiers, which are priority. If a higher tier survey can take an observation, even if it's a lower priority for that survey than one in a lower tier, the higher tier survey will win. So tiers prioritize, and then within a tier, the surveys compete. All right, that's the basics. The next thing is, what are surveys? So not every survey makes decisions in the same way. And this is not just true of like what goes into the decision in a particular survey, but that they also have different decision-making methods. And so Peter says, it's a modular decision tree. So we have some of those modules are the tiers, and then within the tiers, the decisions from the surveys. But also it's because there's a modular range of surveys. So we have things like scripted surveys, which take a list of desired observations, along with some constraints like the time window, the hour angle, what the sun altitude is. And then it will try to acquire the observations in that list when the constraints for that particular observation is matched. So we use this for the deep drilling fields. You could also use it for engineering tests, and there's lots of use for this, but it's a very sort of prescriptive survey. If something can be done, it will, basically. And then we have Markov, which is we actually have many subclasses of this kind of survey. It's basically saying this is a survey that uses a lot of basis functions, potentially a lot of basis functions, to make decisions about which observation to take. And we use these for a wide area survey for the most part. Sometimes we use them for more like a single pointing, and those are field surveys. They're related. It's just they only have one position on the sky. For field surveys, you can put in a sequence to be obtained every time that survey would request an observation. For the Markov surveys, it's more like you choose one observation, but you can choose it based on anywhere on the sky. Now, really, to fully define a survey, you also and to know like this survey is this survey and not a slightly different survey. You do have to dig into all of the basis functions to say like how is this survey making its decisions. I am not going to go through all of the basis functions for every survey here because that would not be interesting to people and it would be very long. But for now, let's just say that for most of the Markov-based surveys, the typical balance we look for is between the footprint, the what we call M5 difference, which is the 5 sigma point source limiting magnitude that we estimate you would have now over the sky versus the dark sky depth. So it's an estimate not just of where you have the most limiting magnitude right now, but also just compared to what that would be under dark sky conditions. And then we have a slew time basis function. And these are sort of our big three you can think of as like, if you have a wide area survey, these are the big three basis functions that you'll be trying to balance. And it goes so that you can balance even coverage, efficient observations with the slew time, and photon collection with the depth. And there's numbers that you can use to change how these balance against each other, for example. And these are all some of the things that go into making a full survey configuration. But this is the basic. And then another thing we do for this use at the summit is we have some standard masks, which we apply to every survey. And these are basically that we're putting in the administrative constraints or the just general a little bit more than that because of Venus and Jupiter, but these are constraints that every survey will follow. So we have avoiding the moon by about 30 degrees. Every survey will respect the altitude limits for the telescope. So we don't, so this will mask off the sky below our lower limit and around zenith. And every survey in the FES avoids Venus, Mars, and Jupiter, primarily because they're so bright and they move fast. So it's just not worth us looking at them. And we can also add temporary masks. So for example, if we need to avoid a given azimuth range on a particular night, we can add this in. All right. So that's the basics of what goes into um, our FBS configurations on the sky. And like this is the specifics for what we have now in V5.3. So you can see there's a lot of things on this list. We have 8 tiers. And then within those tiers, we have 40 surveys, but all those are not necessarily in the same tier. So those 40 surveys aren't all competing against each other. They're only competing within their same tier. Okay, so when we say this is what the FES is doing, what we mean is at a particular time, the FES gets updated with the conditions. So where the telescope is, what the seeing is like, what the weather's like, what the sky brightness is. Um, and then it goes through this list of tiers until it comes to a tier that says, yes, this is perfect. I can take an observation now. And then that tier will choose an observation for the survey, for the whole survey. This is where it gets a little tricky. So we have our survey objects, and then we have the survey we're doing. But here, I mean, I'll try to make sure I'm saying survey by the survey objects. So these are our tiers. I'm going to go through each tier and just say this is the kind of observations this would take and what they look like in our 5.3 simulation. So we have the target of opportunity tier, the TO tier. This is a set of basically a set of scripted observations that are waiting for information that says, oh, this event happened. If the event matches the type of object it's supposed to follow up, then it follows the scripted, the predefined observation plan, which comes from the 2024 TO workshop report. So this is a top tier survey, the very top tier. So if a TO event comes in and a survey, one of these TO surveys matches the event and the observations are possible, like the list of observations from a scripted survey says, yes, this matches the conditions, then this will be the next thing that's observed. I'm going to introduce here not just our sky plot on the left, but on the right. This is an LTAS distribution of where those observations were in V5.3. So you see these are being picked up over on the left. You can see over it very much all over the sky, and that's by chance, of course, because we don't know where the real TOs are going to be. And on the right is like telling you where, from the telescope's point of view, it was observing in order um, to see these TOs. Our next tier is a survey that's trying to coordinate with the Roman galactic plane field. So this results in it's set up to obtain about just over 2,000 visits spanning 5 years. This is frequent monitoring while the field is available, so and it goes through GRIZ bands. And the idea is to coordinate with Roman. This does not request any observations within year 1. And it is a survey that we need to update and make sure we're actually coordinating because we don't have this full information yet. So these observations in the full 5.3 simulation are a little bit of a placeholder, but it's about what we want to do. Our next here is the deep drilling fields. So this is a single scripted survey containing all of the predefined DDF desired observations. So this survey is configured a little bit differently than a lot of our other things. For a scripted survey, you basically can give it a list to say ahead of time to say, here, these are the observations I want to take. Please try to take these observations if you can. And obviously, each of those observations come with some constraints, the most important of which is usually the time window that that observation could be acquired in. So to set up our desired DDF observations, we optimize those independently ahead of time. And this is so that because these are a very limited set of pointings, we can do this. We can say when would be the best time to observe this field when we have this particular number of observations we want to get in the season, with some cadence constraints perhaps, and then pick the best time in the night based on the sky brightness to obtain that observation. And also that way we can skip times when the moon is bright and so on. So the DDFs are handled a little bit differently than most of the other things. We're going ahead before we even get to the survey to say this is when we should take these observations over the season. Obviously, we don't know when the weather is going to be good or bad, but that's where the scripted survey can handle that because you can give it each of those observations a time window of when to actually run. So when we set up our list, we take into account the time window and flexibility, for example. So we have again on the bottom here the RA Dex distribution on the sky for the deep drilling fields. I think this is fairly familiar to most people. In the middle, the distribution of those visits over altitude and azimuth. And this is kind of interesting because you can see that there's this little hole in the middle. You probably can't see my mouse cursor, but there. Anyway, that's the zenith exclusion region because we can't track the telescope through zenith. So we can observe on either side of zenith, but not right at zenith. And then on the right, here is now another new plot. So what this one shows is on the y-axis, it's time away from local midnight. And on the x-axis, it's just basically the night of the survey. So you can see the length of the night changing over, this is just the first 2 years of the survey. So you can see the length of the night changing as with those red lines getting narrower and then wider. And then the times of the deep drilling fields and their filters are shown by the little lines on the inside. And it is a little bit hard um, to there's a problem with like scale and how much data you're trying to show. So some of these points in the plot are not super easy to see, but hopefully you were able to pick up the link to my slides. But what you can see here is that as the field becomes available, we observe the field at the best time of the night for the time where the field is visible. And then you can see the similar thing happening for like the other fields because this is all the deep drilling fields together. They're not quite at the same RA, but they're very clustered. And then again, the same. So that is all of the deep drilling fields. So they have slightly different RA ranges and times. But you can see how we're observing at the best, hopefully at the best time of the night for all of those that we've chosen the time when the sky brightness is the best. All right, so right, I need to say a little bit more about the deep drilling fields. For each deep drilling visit, we have rotational and translational dithers applied. It's a 3-degree rotational dither between visits. So until we change the filter, we just click along by 3 degrees. And then the translational offset is a radial dither around the field center of 0.2 degrees. For the Euclid deep drilling field, it's a little bit different because we don't do a radial dither, we do dither towards the other field. But it's it's easier to just describe these for the rest of the deep drilling fields. The sequences for these, the sequences we set up in the pre-calculated request, so this is what we're trying to obtain, are in deep seasons. Those are the shallow seasons or deep seasons. Um, it alternates. So on even days, we would get 2 visits in G and 2 visits in I. And on odd days, we'd get 2 visits in R and 2 visits in Z. And then every few days, so that it lines up with these, but is not quite every day, we have 3 visits in U and 2 visits in Y. So as I said, we have time windows for each of these, so you can think of them as expiring. So the even and odd don't build up over multiple days. They expire very quickly. The U and Y expire a little bit more slowly, so they can occasionally double up, and so we would get 6 in U or 4 in Y. For the EDFS field, the sequences are the same, but the cadence, the frequency is slower to accommodate the double pointing. And then in ultra deep seasons, we still have the same even odd day sequences, but then we also add frequent but not everyday sequences of 8 in U, 4 in G, 18 in R, 55 in I, 52 in Z, and 20 in Y band. So this is um, very red heavy. And the idea is this is looking for high redshift supernova. All right. Now we move along to the template tier. Please do go ahead and raise your hand if you have questions while we're going through here. Okay, so the template tier, this is our new tier in V5.3. We're acquiring visits separated by about 25 minutes in good image quality for the template tier. And you can see the names of the filters that are paired together for these pairs in the list up at the top. So we have U paired with U, G with G, G also with R with R and I. So in general, for our standard pairs, we don't pair the same filter with itself, except for Y band. But for the template tier, because we're trying to get the U band images under tighter constraints for the image quality, we do pair U with itself and G with itself. Um, so the template tier will only request observations when the atmospheric seeing, as we're getting the measurement from the DIM currently, implies that the predicted seeing, full width half max, sorry, for the next visit would be better than the equivalent of 1.2 arc seconds at zenith. And this is a little bit, tiny bit tricky to explain because when I say 1.2 arc seconds at zenith, we do let that vary with declination. So I have a plot on the right of what a 1.2 full width half max at zenith translates to over the declination range of our footprint. Because obviously at higher dec, you don't get as good seeing. And so that the template tier is looking for the declination appropriate predicted full width half max at its location, and it will also only track observations which meet those full width half max requirements. There are also some hour angle limits to make sure we're pushing towards zenith, and there are some additional constraints. Otherwise, many aspects are similar to the standard pair survey. The template tier is important to note, shuts off when 6 visits with the desired full width half max are acquired, or at the end of year 1, whichever is soonest. And this is in our 5.3 configuration. This is the kind of thing, like the details of what is the cutoff at zenith and how many visits we need and when should it cut off. Those are things that we'll go back and adjust as we sync up better with data management pipeline and requirements, and we see what they can use. The template here, so this is the footprint again on the sky in our deck and the footprint in altitude and azimuth. So what you're seeing here, that wedge shape is the hour angle constraints. And then on the right is that same plot of like when the observations are happening. And notice this one's much shorter in time because it only runs for the first year. You can also, now that there's more observations on this plot, you can see um, a blank period here just shortly after the start of the simulation. And that's because we have a downtime period there in the simulation. You also can notice that this is taking up most of the time of the survey. Um, Not all of it, but a lot of it. And actually, now I think about it, see if you notice this stripe going through here, oops, um, that would be because that matches up with our deep drilling fields in the previous plot. And when the deep drilling fields are intensively taking observations. Okay, our next tier down is triplets because we have a desire to get a few hour timescale follow-up. So what that happens here is we have a pair taken near the start of the night, which then triggers a follow-up visit 2 to 7 hours later in one of the same filters. So the first pair is GR, RI, or IZ, and the follow-up visit is in one of those same filters. The pairs come from a standard pair survey, but only runs once a night, only once every 4 days, so there's more time constraints. And the third visit comes from one of these scripted surveys, which says, oh, you took an observation, let me put that on my list to follow up. There are some hour angle constraints on the first pair, so that we push it into parts of the sky which are rising, so we don't accidentally like make sure that we couldn't observe later. And then here you can see what happens. So we have the first pair being pushed into the parts of the sky that are rising. And then you have the second visit of the pair, or sorry, the triplet after the pair occurring at a wider range of positions on the sky. Because of that, it could be anywhere from 2 to 7 hours later. And then these are the same plots here, but this is the first pair. So you can see it's stacked up near the start of the night and only happening once per night. And then the second survey, triplet of the pair happening at various other times during the night. Okay, and now we come to our pair survey, which is fairly far down in the tiers, but this is actually the workhorse of our survey. More than 60% of the visits actually come from this tier. This is the standard pairs all over the sky survey that we have. So this is where we're balancing the M5 difference, the footprint, the slew times, make generally balanced choices, and then we add some extra basis functions to do things like make sure we get at least 4 visits per pointing in each band per year, so that we don't try to take more than 2 visits per night at any point in the sky. The pairs are the first visit of the pair is followed by a second in a different filter, and you can see the filter combinations up at the top. But and the goal revisit time for the second visit in the pair is 33 minutes. And you can see on this plot here, which is over the whole sky, what is the typical time to coming back to the field, that we do have this good strong peak at 33 minutes. You also see this peak here, and this is just because of how this metric works. And this is from field overlaps. So when we take a visit, we're most likely to take the next visit right next to it. And then that gives us a little bit of overlap. So that has a very short interval between visits in there. So at 5.3, one of the new things we've done is that the visits in the pair, the interval is trying to make 33 minutes, but it will scale that slightly depending on the best visit time available. Sorry, how to best fill the time of the night. So the goal is 33 minutes. That's the most common time, but it can range coming from the same survey anywhere from like 20 to it's 40 or 45 minutes or something like that. So it could be a little bit longer depending on how much time you have in the night. This replaces if you we're more familiar with our old survey configuration. We had this 15-minute pair and a 33-minute pair. We've consolidated them with this dynamic time scaling. We only have this one pair survey now. So this is good. Simplifies life. How are these observing over the whole sky? Pretty much everywhere. And then on the right, you see the same plot of visits over time from 5.3. And notice there's very few visits in pairs in the first year. And that's because most of the time we're taking templates. And then after the template tier shuts off, we start taking pairs, the standard pairs. Remember, the templates are in pairs as well. All right, now we have one of our microsurvey tiers, our only microsurvey tier. And this is the Twilight in Your Sun microsurvey. It takes observations in RI and Z. It's trying to get low solar elongation near the ecliptic observations during twilight. So it runs, it will only start if the sun altitude is above -15 during this time period. And it does short exposures, 15 seconds. So it runs in the target area, defines a target area. One of these RIZ will win in that tier, and then it will try to get 4 images per pointing in the target area. And the area means that the total time we need to complete the whole microsurvey in like the morning or night of when it's triggered is about 20 minutes. So these do successfully get low solar elongation visits. You can see that on the right. And you can also see that these are being pushed to the far edges of the sky. And this triggers in the morning and the evening, but not every day. It's every 4 days, I think. Yes. All right. And then the very last tier we have is the greedy tier. So this tier serves as a filler when no other survey can schedule visits. The greedy survey is there for you. It just schedules one visit at a time. It doesn't have a lot of other time constraints. It sort of is discouraged from revisiting the same part of the sky more than once in a night. But other than that, it just is going to balance what's the depth, what's the footprint, what's the slew time, so that it can make generally balanced choices. But there are no pairs required. There's no you must finish because it's only one visit. It doesn't have to consider too far into the future. And so a lot of those other basis functions from all of the other surveys have dropped. It's simple. You wouldn't want to take most of your survey visits like this because it also does things like get trapped in particular areas of the sky. But yeah, this is our single visits over the sky, backing up everything else. This runs in RIZMY. Look at that. I made it through all of the tiers. I'm actually going to talk a little bit about like what else went into our simulations and what we didn't know next. So if there are questions about like the survey configuration itself, the scheduler configuration, could take just a quick moment. Oh, David?
Yeah. For the wide, fast, deep survey, then that's the combination of the template survey and then the para survey?
So this is a great question, actually. I didn't really so the wide fast deep is more of like an area and goal number of visits over the sky. So when we define the footprint that goes into the greedy survey or the pairs survey or the not so much the template, but a little bit the template. But when we define the footprint that goes in here and the greedy survey, we use our footprint over the whole sky. And so the wide, fast, deep footprint is encoded into that information that we pass to each of these surveys. So the wide, fast, deep, there is not really a survey that is charged with acquiring wide, fast, deep from the scheduler point of view. the where this comes in is that we, as the survey strategy team, know what our coverage should be, and so we say, yes, that's what the footprint should look like, so that we do have a wide, fast, deep area, and then we place that into the footprint. And because we know we want pairs in the wide, fast, deep, we arrange things so that the pair survey gets most of those visits. So from within the scheduler configuration, there really is no wide, fast, deep versus north ecliptic spur. But that all goes in as part of the information we feed into the survey.
So sorry, just a quick follow-up. So, but it must be that things like the twilight observations wouldn't count towards that coverage.
Yeah, so also a good question. This is true because every one of these surveys that I talked about, you not only have the option to mask off parts of the sky, but you can also tell it to ignore certain kinds of observations. So there is a piece of metadata that actually gets into all of the information from the visits that is later available to everybody, called the scheduler note. And this is our piece of metadata that sort of tracks which of these surveys it came from, and sometimes extra information as well. And so when a visit comes from the Twilight Near Sun survey, it carries a piece of information that says this came from the Twilight Near Sun survey. And so the pair survey is told, ignore those. Those are not relevant for you. You don't use that to build up the footprint. Um, so that's how this works. And we also tell the pair survey, for example, to ignore the TOs observations, because they were putting dents in our footprint. And so there is a lot of room to go in and think about, like, how can you change how the survey is behaving. And this is one of the challenges, but also one of the strengths about the FBS configuration. There's usually more than one way to do a thing. All right. So I will, unless there's other questions, I'm going to go and talk a little bit about, like, so yesterday we talked about the V5.3 simulation. We talked about, oh, there's 10% less visits in the 5.3. Yes, sorry. So Rob pointed out the triplets tier also contributes to wide fast deep. There's a lot of things that contribute to wide fast deep, and even the greedy survey does. So yesterday we said there's 10% fewer visits in V5.3. And I just want to take a moment to acknowledge that this, as Jaco did as well, right? We don't know what the weather is going to be. We also don't know some other things. So the visit gap, the time between visits we talked about yesterday, um, I said it has some overhead that's for every slew that is kind of variable. And at the moment, I think that variability might be, at least might lead to a variation in the total number of visits, that it may be that we get the number wrong by about 10%. That might be not be too high right now, but after 6 months, I think that we should not be, like, incorrect by this much. And not just because we will know better, like, how the slew time is, but because the slew time itself will improve and match our model. But we don't know exactly how fast that's going to improve. And so we didn't put it into the simulation. So in the first period of time, our rate of acquiring visits in the simulation, V5.3, is probably a little bit too high. The actual engineering time needs. So we put in 2 half nights for the first 6 months, but that could be 2 full nights for the first 6 months. And so that kind of gives you that we might be as much as 15% too high in the total number of visits in the first 6 months. But after a full year, if we're not doing that engineering time anymore, which we is not the current estimate, then we wouldn't be that incorrect. That number reduces over time, right? Also, it doesn't take into account that we might get science images from those engineering tests because sometimes they do run the FES during their engineering night. Sometimes they run the very specific kinds of observations that are still valid observations for engineering. So there's sort of uncertainty here about what will happen with that engineering time and what use it might be able to be used for. There's the fault downtime and time scale of improvement. So we do have a model for faults in V5.3, which is an improvement over our earlier sims. I do think it's more accurate and relatively accurate, but there is a lot of variability on this. And so this, I think it's a little hard to say. I'm hoping we have guessed fairly right, but it's hard to put a number on how accurate or not accurate the values we've come up with are. Then we have the system contribution to seeing and the timescale for improvement. So we're just not modeling this at present. We can look at doing that, especially during the first year, but also we don't know the timescale for that improvement or what will happen there. Most likely, as we get more louvers, we'll see changes, and that will be something we track for sure. But then we have the effects of cloud transparency, which we don't model at present, and dodging clouds, which we're working on, and we actually have a couple of things in active development, but certainly is room for future improvement here. So. And then the last thing is the weather downtime. So we don't have any clear indication of issues, but obviously we'll be monitoring this. So as you look at smaller and smaller chunks of time out of V5.3.1, I think your uncertainty is higher, right? As you look at the full 10 years, that's probably not as uncertain as if you're looking only at the first 6 months. So I think this is the main thing I wanted to say here is just to make sure you understand, like, if you're looking at a small time scale, the uncertainty is definitely higher. All right. We took a couple questions along the way. But if there's any questions here, and then I have taken up most of the question time with the presentation up to this point, but we'll move on to TOs a little bit late, maybe. Okay. So if there's any questions or comments about this part, we can take them here. Or not, eh? Okay. Well, in which case, I'm on time. So, targets of opportunity. We have I talked about the target of opportunity tier and what it, just briefly, like how it works. Like we have this list of scripted surveys that are all in the TO tier. They would compete against each other, but it's just that we don't expect to get multiple TOs at the same time. If we did, they would just queue up behind each other. Up to 3% of the survey time may be directed to TO follow-up. The general plans for TO follow-up at present are well described in this 2024 TO workshop report. There is another follow-up report. So Sean McBride has been doing a lot of work with the observatory to sort of pull in the different TO workshop report and the very few cases that we didn't simulate because they were over large amounts of area. And so there is an update for this somewhere, and I have heard that there was a workshop this year that will probably be looking into updating these follow-up plans as well. But what we have now does match the 2.0 workshop and also some I'll find the link for the other documentation. We have a Rubin TO advisory board. Um, this is a link to their documentation, their charge, and they provide guidance regarding specific TO events. Um, much of the TO process is intended to be automated. So we get an alert from an external program. It's evaluated by the Rubin TOO producer, which is a separate, not FBS scheduler, but it's a Summit piece of software framework. It evaluates the TOO producer evaluates the alert, and if it meets criteria, then it passes the alert information into the FBS eventually. It goes through some systems like the engineering facilities database, the EFD at the Summit, and then it gets to the FBS. Um, and so one of the FBS TO surveys, upon receiving that alert, will create the list of desired observations that match the predefined plan for that kind of TO. And then off we go. So this, if the criteria are defined appropriately, this can all happen automatically and quickly and without needing a human in the loop. Um, the external events that are currently received by the TO producer include gravitational wave events, the LVK alerts. It can obtain observations of potentially hazardous asteroids from JPL Scout, high energy neutrinos from IceCube, and the galactic supernova from Super Kamiokande. There's another event producer that they're working on adding. It should be within the next year or so, but is not available yet. Now, that's the automated route, but if there is an alert or some kind of event that Rubin should follow, but is not one of these automated sets of events, then the TO advisory board, whose members are listed here, will activate, and they will sort of activate that TO, and they can provide guidance on what to do here. So the TO advisory board is intended to provide general guidance on the TO program on short time scales, like less than 24 hours for these things that don't fit into our current criteria and wouldn't match the automated response. They can do medium time scale response for perhaps following up a multi-day TO. And then they also do feedback on longer time scales like weeks and months. And so one of the things that obviously that we will have to do is keep track of how the TO events are performing and how they're matching up with the rest of the survey, so that if we need to go and change the criteria for the automated triggering, then we can do that. All right. The general TO workflow looks like this. So we have our external event producers, LVK, IceCube, Super K, JPL. And then that goes into SIMA. So SIMA hopscotch is where we receive the alerts from. Then this is part of the TO producer, so it parses the alert for quality. Does it meet criteria, or does it meet criteria? Does it fail? If it's failed, it's just rejected. If it passes the quality criteria, then it goes to the Rubin EFD. Then it goes to the scheduler CSC, which is the framework that the FBS runs within at the Summit. And then this scheduler creates an observing strategy. This is the FBS, creates this observing strategy and then passes that back to the scheduler CSC, so Rubin executes the observation. And then afterwards, we have all of our processing to understand what the alert is. I pulled this image from Sean McBride's SBIE paper for this year, so this is hot off the press. And of course, the TO advisory committee can decide to observe a non-standard TO. Yeah, during commissioning, we did get a chance to test this workflow. It was not as automated as some of the previous as the previous steps may have implied. But that was kind of on purpose because we were in commissioning and we didn't want to just be passing through alerts unexpectedly. So every alert that was actually passed to the FBS was done by hand. So we didn't get more than we expected. We tested the TO workflow of passing the alerts through the EFD and into the FBS on well, actually three, but let's focus on these two, which got more observations. So there was 3i Atlas, and this was a very successful TO program and resulted in, I think, probably the first paper coming out of ribbon commissioning in the SV survey over the summer. This would definitely have been a non-standard TO no matter what. But we did observe it several times. You can see the observation footprint here. This little spot here was we were testing this by hand, remember, and this was not a mistake. It was just that we on one night we tried to observe this field, and our masks in the FBS did their job and said you cannot observe that field right now because it's too close to the moon. And so they said, okay, we still want to test the TO procedure, so we're just going to put a different pointing center into the information we pass to the FBS. So we have this thing here, which we should have updated the labeling for, but we didn't, and so the commissioning, right? But I thought it was really great because it also illustrated the FBS is doing its job with the masks, and it's making sure that um, we're not doing things that the telescope is not supposed to do. Um, on the right was our bigger follow-up TO. So this was gravitational wave candidate S25112 CM. We do have some work to do on our metadata because it came through looking at like one. But we actually we fixed that already. We just haven't had another chance to test it. So this TO was a gravitational wave that had a very large footprint, and it covered the whole sky almost through here. This is the what we deemed at the time to be the high priority area of the footprint, with some over here. So this, in this case, this was not a mistake. It was just a very far part of the footprint. And we observed this TO for a couple of nights in G and I band. And so we followed this area, we did it again, we did it again. And so this was following the planned observations. One of the things about the 3i Atlas being a non-standard TO is that we had to actually put in the observations we wanted because it didn't really, we had to make it look like one of the cases we expected. Okay, and over here, this one did, so we followed it. We found was that there were some details about how the FBS runs at the summit that are a little bit different than how it runs when we run it in a simulation. And so there were some things, there were definitely things we learned from this experience. It was also really good to see us follow this large area. I think it has proved difficult to process this without uh, like production grade templates. And so we'll see how that goes. Okay. So we have excuse me, we have children. Um, so we did the gravitational wave case, and we learned things, and we're implementing updates for this in the FBS. And then we have questions for any of this so far. Oh, Roberto.
Yes, thank you very much. Just a couple of very quick questions. So, is there I'm thinking mostly of sort of gravitational waves. follow-up, is there a ramp up considering the number of requests towards the later years? Because I will assume that sort of this will keep increasing and increasing.
It kind of goes with the observing seasons for LIGO, Virgo, so they're not actually spread evenly throughout the whole survey, and they
Mhm.
are concentrated in, I think it's year two. Peter might have a better answer on when exactly it is. But they are concentrated in time. This is also something we'll have to consider because obviously we've said, okay, this is when we think that the alerts will be coming in. And we've based that time span and the rates on what came out of the TOO workshop, but
Mhm.
we don't know for sure.
Okay. And can I ask one more question?
Mhm.
The So, right, a lot of what happened by the change to 5.3 was this the last 10% lower on sky time. So I'm wondering, is it too difficult to sort of after the fact see if the images obtained for TO could fit within the strategies of the WFD and the DDFs? It could add to zero because we don't know where the TOs will be and when they will be. But
Yeah.
if they add, that will help recover some of that.
So potentially,
Mhm.
um, I mean, and it's difficult because when we're observing, like with the pairs survey or all the other tiers that go into making our normal observing mode, we don't really have a way to force it to say, okay, on tonight, actually really go do this part of the sky. So you would still be activating a TOO essentially. And what it would be is maybe what we would could do is make the TOO gentler, but that's kind of the opposite of what you want for the TOO, right? Um, so so there, yes, there is this tension between like um following up the TOO as it ideally would be and as quick as it would be versus like doing it in a way that might just look like the normal survey. Um, and the looking like the normal survey is not, yeah. We did have the reason originally when we made TOOs, we counted them towards the footprint for the pairs survey, but what we found was that disturbs the cadence we're trying to get with the pairs as well. So it's kind of like they don't go together super well, but certainly, if this turns out to be a really big problem that we really have many more TOs that we need to follow up than we can accommodate. This would be something we could go and revisit, but it is difficult, and I'm not sure it'd be successful.
Thank
Um,
you.
Bindu?
Yeah, hi, Lynn. Really quick, is there a fixed amount of time assigned for the TO observations? And if it is there a plan like, in case if that time has not been used, how that time will be used otherwise?
Yeah, good question. It's not, there is a fixed cap. Well, in theory, a fixed cap is we don't enforce it in the FBS. To enforce the cap on the TOs, it would have to come into like the criteria for triggering on the TOs. So the TO program is expected to use up to 3% of the total survey time. There's nothing that like if there are no TOs, it's not like we're not observing. We just don't observe a TO and we do observe all the normal stuff we would observe. So all of the other tiers lower in the scheduler just would activate. And like I was saying yesterday, our footprint is just a ratio. So if we have more time, we just get more observations distributed over the footprint. And if we have less time, we just get less observations distributed over the footprint.
I see, thanks.
So it just, if we didn't have any TOs, we would have a little bit more time that would go into everything else in the survey. And if we had more TOs, then it takes the time away.
Thanks.
Rachel.
Yeah, hi, Lynn. Just to add to that and make sure I've understood properly, especially given an answer you gave to another question. Is it correct that, like, since we do anticipate that the number of gravitational wave events will depend on like whether there's like a LIGO Virgo Cagra observing run on or not, like there might be some years where the TOO time could exceed the 3%, and the 3% is more across the whole survey.
Yeah. Yeah, I mean, we do expect it to be variable because most of the time in the TOs is for these very large events, which are not as frequent. So they will be bunched up. Sorry, not bunched up, but the TO time overall will be bunchy. I don't think we have a cap on how much TO time can be used within a particular time frame. And that is something that I think the SEOC have decided to think about, but it is hard to make progress on that without understanding what the actual event rate is going to be, because there's uncertainty on it. So, and it's also hard because it is hard then also to say, okay, what effect will that have on the rest of the observations? So yeah, I do think this is a thing that we need to think about, because it would go back to the TO advisory board, and they would say, hey, this time is being used too quickly, and we should change the criteria. Igor, and you are on the TO advisory board, so hopefully you can say a few words here.
Yeah, maybe just complementing a little bit all you've said also in response to Rachel. We have tried to rally up the community, bringing it together to discuss and develop strategies and come up with realistic budgets for TO observation requests. So this was done in 2024, and we are doing it again right now. Hopefully we will have the new documents published by the end of July. So I would suggest if you want to have like a preview, you can check on the archive. We have put the report from 2024. I think if you search the Rubin TO program on ADS, should be the first thing that comes up. Otherwise, waiting a month, you will have more solid numbers. These numbers that we've come up with try to be more or less within 3% over the course of the whole survey. We are trying to be very mindful of minimizing disruption, of course. And when I say we, I really mean everyone who is interested in TOs, from gravitational waves to other type of messengers to potentially hazardous asteroids. In addition, at the moment, the go-to policy is whenever a counterpart we're searching for is found, we stop observations so that other telescope with a smaller field of view can perform the follow-up if they're available. So there are, I think, there are ways we're actually going to perform the observations that are maybe not fully encapsulated in the simulations, because again, they're so honestly so difficult to predict. But my hope is that we will use the time well in a very efficient manner, possibly all what's available, and if not, observation will go towards the minimum, all the meaningful science that can be achieved with the regular survey. And all of this keeps changing. The rates, for example, for gravitational wave sources keep changing as more and more LIGO runs are performed. And at the same time, new ideas for interesting science cases are brought up by the community. So every couple of years, we will try to rethink a little bit how to structure the program and try to make it as effective and efficient as possible.
Thanks, Igor. I'm glad you got it, that we got to hear from somebody from the TO advisory board. Yay. All right. And now we can move. Oh, sorry. Go ahead, Rob. We can take one more question here.
Yeah, I just wanted to follow up on a little bit on Roberta's question. One of the things about the TOs, and I just checked in with Peter about this, was some of the observations are using non-standard visits. So the exposure times might go up to 120 seconds in the TOOs. And so, whether those could be included in what becomes wide, fast, deep, yeah, I mean, maybe, probably, but that they are a little bit different than the other observations in the survey, or can be.
All right. Excellent. And let's move on to talking about the templates and the template tier. Eric, were you
I'm
Eric?
here.
Oh,
Yeah, I'm
great.
here.
Okay. I wasn't quite sure where to put in your slides. I was just going to say a little bit about our new option for the template tier, and then hand over to you for that.
Sure, that's fine. How much time do you want me to spend?
Um, you said you didn't want very long, so I'm thinking you can somewhere between 5 and 10 minutes. If that's
Okay, that sounds fine.
And some of that might be questions if that works better. Okay, so some of this Eric is going to just say yes or no about, but basically one of the issues we have is good template creation requires at least 5 to 6 visits with the full width, half max, and transparency required for the template coad, and that's these are declination dependent and band dependent values. Now, the other thing is, why can't we just create bad templates and keep going? Well, bad templates are bad because replacing templates is bad for it adds offsets in the magnitudes of the alerts, so the template continuity over time is strongly preferred. And then the other thing is bad templates make more alerts, which then make even more alerts because of how the alert prompt processing pipeline works. And this basically just loads up the prompt processing database with noise. And so we don't want to just make bad templates and keep going. So we want to make good templates. And then the problem is, if we don't set up the FBS to sort of have a specific push to acquire the 5 to 6 visits with good image quality and good transparency at each point on the sky per band, there is a high likelihood that we will not acquire those necessary visits within year 1. And this is not just a high likelihood, but almost certain in UNG without the template tier. So this is why we added the template tier to the baseline surveys, so that we meet this need. Now, the thing we immediately did was we just put in a template tier which acquired visits in singles, but because there's so many visits in this tier in year 1, singles were not a good choice. So I keep saying we acquire the templates in pairs because that actually was an important consideration. The next question is, can we improve on the template acquisition? Because there is still a risk that we would not complete the templates over the template inputs. We don't make the templates, that we would not get enough template inputs over the whole sky at the end of year 1. So we have a simulation called faster templates. This is in our v5.3 set of simulations. And the idea here is we need epics with dithering for the pixel coverage. Individually, they could be shallower, potentially, although they shouldn't be worse quality full width half max. But because they are good quality full width half max, perhaps they can just be a little bit shorter exposures, and it doesn't make them that much shallower in depth. So this simulation poses a question: what if we take the template visits as 20-second images, increasing the number of epochs, as versus what we would have if we just took them as 30-second visits. Now, so U-band is special as always because U-band is 38 seconds in the standard visit, and it would go down to 25 seconds in these shorter visits. Now, this is not just for us to say, because there's lots of impacts to everybody else. So we have an RFC, a request for comment, in progress within Ribbon to evaluate the possibility and impacts of making this change. And I will just note that 70% of the first year images in the simulation are acquired with the template tier. So when we say, oh, you could just take some 20-second images, we actually mean the majority of the images in year one would be these shorter images. The impacts on our metrics. So if you remember this grid from yesterday, we have the high level metrics across a bunch of different science areas. So these are at the bottom are the SRD metrics, and we have things that go into cosmology and then time domain and static science and galaxies and solar system objects. And this is all normalized to be 5.3. And here we have what happens if we go to these 20-second templates. So the 20-second fast template simulation. Some things get better, some things get worse. It's not obvious we've completely captured the effect in our metrics. But one thing that is for sure is that on the right here, what we have is the night that you have captured a given amount of area while getting at least 4 visits per band onto silicon. So this is math evaluating the camera footprint on our visit bore sites, which is not quite the same as how, as I mentioned yesterday, as how data management would count whether the detector was usable to go into the coad, because they have probably different constraints on the edges and things like that. So this is our estimate, but it's not the final answer. So this is if we have this deck dependent seeing limit, and we said it's a limit of 1.2 arc seconds at zenith, and how much area would you have where you got 4 visits onto silicon and per band. And so what you see is this is the total area of the survey, and if with the comp survey v5.3, that's the one where we use the old downtime, so we don't have our extra downtime. It's blue. The green line here that's lower is our baseline 5.3. So this is the effect of not having as many visits in year one. And then the red line is what happens if we take those visits and make them shorter. So with a shorter visit, we do have a little bit less duty cycle on the sky, but we still end up with more visits. And so if we were to do that and all of the things like the visit gaps remain the same, then we would push back up to the same number of visits as we would have had without the extra downtime. And so this is close to, this is essentially getting templates over the sky by the end of year one. Now, like I said, this is uncertain. You can't say, oh, if we don't do this, we won't close the sky for the templates, and if we do, then we will. But that's and if you said instead of 4 per year, you said 5. Sorry, 4 per band. You said 5 per band. The difference between these would scale similarly, but it's true that the overall area would be slightly different. All right, so that's ours from the point of view of metrics. Now, is this? So now I'm going to hand it over to Eric to talk about actual templates. And did you have slides of your own that you wanted to talk?
Yeah, I can share.
Perfect. I put this one in because I wasn't quite sure.
Yeah, I'll put them into the shared slide deck after I talk. I just didn't have the link in time.
Perfect. Yeah, sorry about that.
That's okay.
I'm going to stop sharing and hand to you.
All right, so I'm just going to spend a few minutes talking about templates from the data management perspective. So I think it's worth saying up front, kind of distinguishing in our minds two separate questions. One is thinking about what we're aiming for at the end of year one for the inputs into DR1, which has been kind of targeted as our source of good all sky templates. And so that's I think especially driving some of the questions around the template tier that Lynn is describing. How do we get to an endpoint where we have enough inputs of good quality over the whole footprint that we can co-add. Separately, of course, I, like all of you, am extremely excited to get alert science going early in the survey in this first year. And so for that, we need to be even more sort of aggressive in getting templates deployed. How do we maximize that sort of science ahead of DR1? And so there, I think it's clear as you're going to see in a minute, we have to accept some compromises of some kind, and it's just a question of it's kind of an engineering and science trade-off of where do we cut the corners because we don't have as many images as we'd like, and we have to kind of figure out what to do about that. All right, there are kind of two technical constraints that really influence what we do on template generation. The one is for alert production. There's a database we call the APDB, the Alert Production Database, which serves as sort of the core of the association and light curve generation for alerts. And it's very sensitive to false positive rate. If we pump it full of junk sources, it will break down. It will reach capacity and not function. We have approached that on a few occasions and learned from the process, but we have to be thoughtful about it. And I would say, probably as science users, you also don't want just cascades of bad detections either. There's lots of knobs we're learning to tune here, both in things like real bogus and how we configure image subtraction, but. I just wanted to put out front that this is something that we really do care about a lot. And as you'll see in a minute, templates are a major source of false positives. So the other challenge is that it is not as easy as either it sounds or we'd like it to be to change the templates frequently. The processing takes a while, frankly. And so it's not easy to do a big template run and just update things. I also think scientifically, most users don't actually want that because when you change the templates, all the different light curves are going to shift. You get different amounts of contamination from transients in the template for supernovae and things like that, and for variables. So all of that just says that we will change templates over time, but we're not going to thrash them, especially in the first year. So we're trying to do the best job we can, put templates on and keep them there for, of order a year. All right, so since we can't update the templates a lot, we want to try to minimize gaps where we can, because if you have a hole in the template, you can't fill it for a while, you get no alerts from there at all. The fill factor of the camera in terms of when you project it into the template space, it's about 88%. And so if you just use single images, then you're going to just have 12% holes. So we want multiple inputs. And what is the very minimum? If you think of these as just uncorrelated and ask, what area doesn't have any pixels on it, you only need sort of 2 or 3 and you get real close to 100% fill factor. So that's kind of the minimum baseline to if you want to avoid holes. There are some other image quality and image subtraction issues, which we'll discuss there. But in terms of what is the bare minimum for year one, if we accept that we don't want to just leave giant holes in the survey, then there's a few images to input. And again, those should be good quality images. They shouldn't have clouds in them, things like that. As we add images, we do better. With 3 or more images, we can do something, we can do artifact rejection. We have some algorithms that especially work nicely when you get lots of images where it's able to reject footprint detection footprints that only show up in a configurable fraction of the inputs. And so you can see on the right here the difference between sort of mean and sigma clip coads and this what we call compare warp rejection, which is great for getting rid of things like satellite trails and glints and so on. So this is what we why we push for more inputs when we have them. So again, we're trying to get to that sort of greater than 3 images, and that's where we sort of talked to Lynn about, can we get to 5, 6 sort of images to get inputs. All right, what have we done so far? We have DP2 coming later this year, and that is based on commissioning images from last year, which got especially this wide tranche that you see here in the ecliptic plane and crossing through sort of the galactic center region. This is a view of the HIPS maps from the deep coad. The template selections are very slightly different and a little smaller, but it's useful for illustration. And when you zoomed out at this level, it looks great. And you're like, okay, we got templates on all that area. It's not quite that simple. When you zoom in the middle somewhere, you see that, yes, indeed, it is pretty well covered. But at the edges, you can see that these are sort of single epochs that have big chip gaps in them. Don't pay too much attention to the interpolation here, but you can see the chip structure of the camera. This is U-band for comparison, and in U-band, for instance, there's even larger holes even in the middle of this footprint. So as Lynn showed, we have deployed these DP2 templates in addition to the existing deep drilling templates. There's a dashboard that's been circulated, and we're keeping updated as we add new ones. We added a few more from a few weeks ago and are continuing to do so. And so our alert volumes have accordingly increased. What I do want to say, and this again impacts darn it. Let me rapidly edit this. Meant to make that a animation. We do see that even the DP2 templates have some challenges. So this is a pattern of alerts that we've sent out in the last few days. And you can see there's a pretty strong grid structure in some regions of the sky. And this is we have tracked down due to when we have co-added even a relatively small number of images in this wide area, there's a wide enough range of PSF sizes that when you have chip gaps, sometimes the PSF that results in the co-add is printing through has some pretty strong spatial variations, which you can see on the right. For a patch here, I apologize, the full width half max here is in pixel units, which is multiplied by 0.2, but you can kind of see how these structures have the imprint of the focal plane in full width half max space. And so image differencing has a fair bit of trouble right now. It's sort of managing, the kernel is not able to handle such rapid changes, and so you get in excess of false positives. We have a number of ideas about how to deal with this, both at the vetting side and in template construction, image differencing, and so on. But I guess I would just highlight the point that it's not quite as simple as just take 2 images and add them and everything will be fine. It really does. We do see problems. I mean, the good news is these are not such large bogus volumes that it's overwhelming the APDB. But it is something where we feel like we need to take some corrective action. All right, so we're looking ahead to incremental templates with pre-LSST images as well as the previous inputs. Lynn hasn't seen these because I just got them done this morning. So these are plots of basically all of the Rubin science images subject to some cuts, and sort of looking where we could start building incremental templates now. And so this is band by band. I'll call your attention mainly to the green boxes, which are tracks that have complete coverage of at least 3 input images. And so that would be kind of a good place to start. So this is U-band. There's some, maybe, I guess it's labeled here. 42 tracts are maybe plausible. G, a little wider. The white areas already have templates deployed either from the DDFs or from DP2. R band, a little bit of coverage sort of in the south. It remains patchy. There's a region here that maybe we could explore. I-band, there's these big stripes that were taken during OES commissioning, which we can build templates in. So those are a natural place for us to start. Z-band, I think, is in some ways the best. There are some really large areas here that have quite a bit of coverage. And then Y-band a little less. So I think we do have a bit of a head start building templates over a reasonable but not overwhelming area. But we need to sort of understand some of the issues we're seeing with the DP2 templates in order to make sure that we're making the right choices there as we deploy them. So happy to, I don't know if we're going to questions here, Lynn, but that's all I have for the moment.
Yep, it was just questions, and then we back up to the break next. So actually, that was awesome, Eric. Thank you so much. And all of that new stuff, very fascinating. I wanted to make the comment that when we know that we can build a template in a particular area of the sky, we will be able to load that into the template tier survey so that they know that, like, okay, yeah, you may not know about those observations because we're going to wipe its memory clean when we start the survey, but we can tell it, yes, there are already templates available for this part of the sky. All right, David.
Yeah, these DP2 template observations, are that all the range of rotation angles?
Yeah, that's right. That's it's getting the. I mean, maybe Lynn can speak better to it, but my understanding is those are wide, fast, deep style dithers in rotation and translation.
Yeah, so the stripe across the sky in the ecliptic area was mostly wide, fast, deep style. It was mostly coming from our pairs survey tier, but because of the fact that it's a small area on the sky, the repeat rate was a little bit higher, and yeah, but other than that, it would be like our normal survey observations. All right, wow. I really thought everybody would have questions for you, Eric, because of the. That was I'm really fascinated to see where we can go with incremental templates and what we might be able to do even before we start the survey, because these are really big questions, like what are we going to try to do in the first year regarding templates. Well, nobody has asked, but I'm going to ask because I get asked, how soon can you have templates for a particular area of the sky? And I know from watching that can be a significant lag because, as you said, it's quite labor intensive. Do you want to say a few words on like the rate of like once we cover the sky or like
Yeah.
acquiring
So I had this in the slide and kind of brush past it. My estimate right now is that the delta between we know we have enough images here and we could get this into production is about a month. And a lot of that is human steps, either shepherding data through or vetting the data before we deploy it or getting it deployed. I hope that can come down over time as we streamline, our metrics and learn to trust, what we're looking at. Again, we sort of started with the DDFs, which have a very different sort of behavior when you co-add them versus some of these wider areas. So, that's my estimate right now. Is it takes a month, and I hope that it improves over time. It kind of needs to, but I don't think that's happening quickly. So.
John?
So I guess I don't quite follow the big picture case for sort of taking a major part of the first year and turning it into 20-second survey, right? I mean, if there's a 1 month delays anyway on templates, the alert, volume is so large, in the long run, of course, you will have templates and can go backwards in time. So it's just about alert production. Doesn't it seem like there'll be enough alerts that maybe you should just stick with the 30-second? Like, what's the big picture? Like you really won't be able to generate alerts even after 1 year
So,
over the whole sky in every filter? Is that the problem? Like, I
well,
just don't really understand what drives such a big change.
yeah, I don't, okay, so I saw Eric, you put up your hand, so I'm gonna say maybe you, if you have something to say about this, go ahead.
Okay, sure. We can take 2 turns. I think the advantage to 20-second exposures is that it gives you more images, a larger number of images at any given position and filter in the sky at the end of year 1. And if those are, especially if those are preferentially taken in better conditions, that increases the odds that you have a good set of inputs that you can reject artifacts, dither out chip gaps, etc. So you're sort of sacrificing a little bit of depth in exchange for kind of an absolute image quality improvement. It's less about, in my mind, it's less about getting alerts out in year 1 and more about, do you have enough, what is the quality and aerial coverage of templates at the end of year 1? I will say, Lynn didn't say, but we have been discussing in data management, like, can we support 20-second images? Are there concerns we need to worry about? Largely, the answer is no, with one exception. There is some concern that the active optics system, instead of being able to correct sort of every 2 images later, would be then at 3 images later correction because of the shorter sort of cycle time. And that is a significant concern, that they worry that the image quality will suffer. And that may be a showstopper. And there's some discussion, I don't know if Bob or others want to comment, we should just test this. But I think that's maybe the biggest concern that I'm aware of with the 20-second exposures outside of the survey strategy question.
And could I ask a related question? My metric actually seemed to survive because the extra images probably makes up for anything you lose, so it's all fine. But I heard a lot, I think, in previous workshops of the need for really high quality G-band and R-band images, that it was important to get sort of deep, good seeing images there. And it sort of seems like that might be a real problem to what I heard, repeatedly in a lot of documents, that was sort of really a priority for the 10-year static case. Maybe it's all in the wash since it's only 1/10. But is there any comments about that?
This is a good point, because I think that this is one of the things that's not necessarily well captured in the metrics that we have, like how and what it goes into is how well can you deblend things like stars and galaxies is my understanding. Yeah, so that might be an issue. I think it certainly is one of the things we would have to go and consider. It also, after 10 years, it does kind of probably come out in the wash, but the question is, do you need that at the end of year 1, which I think was actually their request, that you have those at the end of year 1. That said, they also didn't have a large number of these. You can sort of think of them as Pathfinder, like they're that's pin deblending based on these like really deep, good seeing images. And it's not obvious you wouldn't have that anyway, even with the slightly shallower depth, because they are in good condition so that you naturally get a slightly deeper depth. So I think that's something to also look at for sure. It's also true that it may be a showstopper based on the AOS. So we'll see. This is still very much in the we're going to have to think about this a little bit more, maybe test some data on the sky. There was another, there's maybe some concern about U-band, and maybe we would have to leave U-band at 38 seconds just because getting even further, getting back into the read noise, which is what would start to happen with a 25-second exposure, might be bad. All right, this is the other thing I was going to say though. It may not be that then if I didn't say, oh, it's so that we can get templates over the whole sky and we can close the sky, but if instead I said, and this might hold up DR1, does that change your opinion? Because that not being able to make templates over the whole sky might actually mean like, oh, we're going to wait a little bit longer until we get those images so we can make them as part of DR1. That is not my decision to make, obviously, and it's not a for sure thing, but like that would be a possibility. So, Dan.
Yeah, so you showed this plot that had the number of, or the area covered versus the number of nights for the various scenarios. And it kind of looked like the slope from the baseline after you reach around 15,000 square degrees was just about the same. And I was wondering, are those the same 15,000 square degrees? Are you envisioning a scenario where you do 20 seconds for like 200 days and then switch over, or?
This one here, you mean?
Yeah.
Yes, sorry. So this would only be 20-second visits coming from the template tier. Any other tier would just do normal 30-second visits. However, like I said, in the first year, and the template tier switches off after the first year, right? So in the first year, on the order of 70% of the visits would be these shorter visits coming from the template tier. So yeah, after this point, it looks it will become fairly similar, but that's also the template tier isn't trying to acquire any visits after that point.
Right. Well, what I meant was after about night 300, the slope of the green line looks basically the same as red, right?
Ah,
So if you were to switch over from 20 seconds to 30 seconds after like, I don't know, 250 nights,
I'm so okay. Peter can say something more about this if he wants because he made this plot, but I'm gonna guess that that's not just because of that a lot of that has to do with how much area is new and what appearing on the sky, maybe rather than quite so much as the rate of acquiring just enough. I'm not sure. Yeah. Peter, do you have anything to say about that?
I bet that rapid rise is that we observed some area at the start of the survey, but didn't get enough to get templates. And so it's come back around. And so now we're able to rapidly, this one image gets us to the threshold. And so that's why there's that rapid rise
Yeah.
there. It's area that's coming back around that now we can complete.
Yeah, that makes sense. So it's because we did part of the sky that we're observing here. We did it back here, but we didn't reach 4.
Yeah.
Okay. I'll pause for a minute if there's any more questions. We are into our break, so but also I think that these are all really good questions, and I really appreciate hearing about the templates and the current plans. So thank you, Eric. All right. I don't see any more questions. Remember, you can ask questions on Slack or on community if you have a more general question. That's great, a great place as well. All right. This is the time for our break. So we'll come back at in 20 minutes at 10 o'clock. All right. Here we are, 10 o'clock. Hopefully everybody comes back from the break now. Okay, so next we have two more specific areas to cover, rolling cadence and options around rolling cadence. And Leanne Guy is going to talk a little bit with us about uniformity in COADs and data management processing for DRP as well to go with that. And then we're going to talk about the DESI survey options. And then we have some time for general discussion as we need it. Okay. So rolling cadence. So if you remember, this is what we do so that we can boost the cadence for time domain in certain areas of the sky at the expense of in other seasons it has slightly lower cadence. So when a part of the sky is in active rolling cadence, the gap between nights of visits is sort of 2 on average. And in a low cadence season, the gap between coming back to the same part of the sky, the same pointing on the sky, is about 7 nights. So it does vary. And then in between, in our seasons, which are just like normal uniform cadence, like in the first year, the gap between revisits is actually median value of 3. Obviously there's a little bit more scatter in there. So if you look at the whole survey and don't look at individual seasons of rolling, you mostly, and you're just measuring something like the gap between visits, you mostly see the uniform seasons, and it sort of washes out the increase from rolling and the decrease from the low activity rolling years. But if you are looking at something like how well you're recovering particular light curves, that will be influenced by the details of the observations in a particular season or year, and so you'll notice that a little bit more. So that's one of the things that, depending on how you're looking at what you're looking at when you're trying to evaluate impacts of just the visit spacing on time domain metrics, you do have to consider whether you're sensitive to the changes in a given year of rolling, or if you're sort of washing out over the whole survey. So that said, that makes some of the metrics a little tough to interpret when you're looking at 10-year metrics. Anyway, what we have is in baseline V5.3, we start rolling after year 1. This is the standard. We don't want to roll inside of year 1 because we want fairly uniform coverage at the end of year 1 so that we can do calibration and photometric and astrometric catalogs over the whole sky with something that's that has the number of visits and is fairly uniform. Now, if we're still acquiring visits needed for the input to templates, instead of starting rolling right after year 2, or right at the start of year 2, at the end of year 1, we could delay the start of rolling until after year 2, because there is a reasonable argument to be made that you should not start rolling when you don't have templates yet, because the templates are needed to fully leverage the time domain, and the time domain is the reason for going into the rolling cadence. Now, it is also too early yet to know if this is a problem, and the decision can wait while we're investigating options on whether we should start rolling at the end of year 1 or whether we should start rolling at the end of year 2. So some of the things we're talking about here in the various simulations that we have are questions of things to think about. We won't be making the decision today or immediately anyway. This series of plots over here on the right is the number of visits in I band. So I chose just a single band after year 1. So year 1 is a time deadline, not a season. So remember, this is just the end of year 1. We would have this many visits in I band. At the end of year 2, our coverage would look like this because we've started rolling during year 2. At the end of year 3, it looks like this because we've started rolling, but also we've started the opposite rolling, but you still see all of this signature of rolling. And then we have a season for the rolling cadence where instead of doing a high activity or low activity, it has an average, so the medium or normal uniform activity. And so that lets the sky catch up and equalize. And so at the end of year 4, we have what looks like a fairly uniform coverage on the sky. Now, I did make these plots removing any of the special surveys because then this lets us see exactly how uniform things like the paired survey and our normal wide, fast, deep kind of observations would look. If we delay the start of rolling until after year 2, what this basically means is we're shuffling the high and low activity and uniform seasons so that the end of year 2 is uniform. So instead of being here at the end of year 4, year 2 would be uniform. And then 3 and 4 would be non-uniform because we've just shuffled that order. Okay. So we have some simulations that illustrate different options. So if you go with the baseline, normally at the end of year 4, we have a uniform data release. And I'm going to keep saying uniform with quotes because this is part of the things that Leanne is going to talk about. We'll talk about a little bit more in a minute. So at the end of year 4, normally we would have a uniform data release. But if we reshuffle and delay the start of rolling, that year 4 uniform data release disappears and it moves into year 2. So these are 2 other options. This is if we just delay the start of rolling, we don't change anything else. So you can see year 4. So across in this plot is all year 4 for different simulations. Down in these series of images is different years. So it's 4, 5, and 7, not 6. I skipped a year, but there. So this is on the left is the baseline for year 4, 5, and 7. In the second row is just a simple, we'll delay the start of rolling for 1 year. So this is what the simulation we're calling roll mash 5.3. So it goes, so this is again year 4, 5, and 7. And you can see year 7, because we only shuffled some of these rolling seasons early in the survey, year 7 looks very similar. So you have year 7 in the baseline, year 7 in roll mash. That's our uniform data release year. And then if we not only reshuffle the seasons of uniform rolling in the first year, in year 2 and 3 and 4, if we also shuffle them in later years, we can move that uniform data release that was in year 7 into year 5. And so this is roll U5, V5.3. So this one, in this U5 simulation, we also delayed the start of rolling for a year. But instead of taking the uniform season right before the year 7 data release, we've moved it up in time. And so we have a uniform data release at year 5 instead. So in both of these simulations, because we wait, we have a uniform data release in year 1, year 2, and then this would be year 7 and year 10, and this would be year 5 and year 10. So if we delay the start of rolling, we inevitably lose uniform data release at year 4, but then we can have a choice about if it's year 7 or year 5. And of course, year 10 in all of these simulations is the same. So because at the end of 10 years, you've done the same number of visits and the simulation is generally the same, just reshuffling the seasons when you're doing rolling cadence and when you're not should be really have a minimal impact on those year 10 metrics. And so this is our metric grid again. It's here's V5.1, the baseline. And so this is what everything is normalized to. And these are these high-level summary metrics. Now, roll year 2, U7 is like we have wait until year 2. This is the roll mash. Sorry, it's renamed. This is one reason why, in general, we discourage people from renaming, but I did it anyway. And this is the one where it was the uniform data release was shuffled into year 5 instead of year 7. And you can see it's not exactly the same. The changes are pretty minimal. So note the scaling here. This is 10% into the red or 10% into the blue. And these are all generally a few percent, except for some. There are some of these time domain metrics which seem a little bit more sensitive. And it may be that what we're actually seeing here is noise rather than actually something real in the changes of the metrics, because really these impacts should be minimal, but it is possible that as we change things around, there's some unintended effects. So it's worth looking at, but it is also possible that's not that significant. So this is the thing we should think about, like, what do we do about if we did delay the start of rolling, which we don't know we would do yet, but it is a possibility, especially if we can't complete templates around the sky at the end of year 1. Then what do we do about later years, and down the road, do we shift some of these uniform data releases around? Now, I also wanted to talk a little bit about uniformity and what that means, because we talk a lot about, hey, let's have a uniform data release, but it's not really very well defined, and it's not obvious what's the best way to support that. There's some uniformity we can enforce, we can try to gain from survey strategy by not letting our number of epochs or depths get too uneven across the sky. And an example of trying to manage that uniformity is with this uniform season in the rolling cadence. There's also an aspect, like, you could enforce uniformity later in the processing chain at data management. Although if we do that there, it necessarily means dropping visits to gain uniformity. So you're not dropping visits completely, but not including them in the coads. So this raises questions: how could or should we achieve uniformity in the coads and the catalogs that come from the coads? What does that mean? There is some natural variation due to weather that will lead to variations in the coated depth across the low dust wide fast deep region. But is it that we want less than 1 magnitude of variation in the estimated coated depth? Is it the number of epochs? Is it a different number on the RMS of the coated depth? And what does it mean for visits which are not included in the coads? So these are all good questions that I had. And then the plots here show us the coated depth and I-band if you do include all of the special surveys versus if you don't. So even if we don't have a question about, like, what do we do with rolling cadence, what do we do with DESI, anything, we already have non-uniformity due to things like the ToOs and other special surveys. So, Leanne, are you there?
I am here.
Excellent, excellent. I was going to hand this over to you now to talk a little bit about some of the things we chatted about the other day, like what happens to visits that don't get included in coads and things like that.
Yeah, okay. Thanks, Lynn. Thanks for introducing us. So I've sort of just come along at the last minute at Lynn's request to support this meeting. I have nothing prepared. I have no answers for you, but I am here to take a lot of questions and to think about how we can address some of the open topics and questions. So what happens to visits that are not included in coads? They will still be perfectly valid single visit images, and there will be catalogs of detections in those single visit images, and they will be included in a data release. They just won't have gone into a coad. You'll already see this, in fact, with Data Preview 2, which is coming up sometime in the July to September timeframe, we have a region of DP2 which has coads, and then we have a lot of other visits scattered across a very large area of the sky. So the coadded region is roughly 3,000 square degrees, although there's variation of coadded depth within that 3,000 square degrees. And then you can get out to another sort of, I think it's about 12,000 or so degrees with just single visit images taken at various positions on the sky. So some of the positions on the sky will only actually have one visit, maybe some will have two, but none of these were coadded. So you'll already see how that looks in the Data Preview 2 release. So the term throw out is a bit strong, maybe. We will throw them out of the coad, but we will not throw them out of the release, provided they meet other quality criteria.
Sorry for my thrashing there as I tried to unmute myself. Yeah, and the catalogs from the single visit images are calibrated in the same way, like against the full astrometric and photometric calibration. Is that
In
correct?
the data release, yes. Like single visit images in the prompt nightly processing, no, have a I think more fast approximate calibration. But in data release, yes, they are fully calibrated single visit images. They're processed in exactly the same way as every other single visit image, irrespective of whether it goes into a coad or not.
So if we were able to make a goal on the uniformity of the co-edited depth, so that when we make catalogs from the co-edited images, that the depth in those catalogs is fairly uniform across the sky. And obviously there's a limit to how much you can do there. But if we were to do that, you would still have all of the single visit measurements well calibrated. So you could do light curve analysis on all of the visits. And it would just be that your co-edited catalog would be more uniform and more shallow.
Yeah, I mean, the co-edited images that are created would be shallower. They would be missing some images. And that would, of course, have an impact on detection in coads, which is what goes into the object catalog. So let's say quite simply, they wouldn't have the same depth. If we remove some, you'd lose some depth. So then you might not have, you might have fewer objects detected in those coads, or their parameters might not be measured with the same sort of accuracy or characterization. There might be more uncertainty around them. Yeah, I think that answers the question.
Let's see if there are questions from the people listening or comments on like what the impact of this uniformity or not is. Roberta?
Yeah, one question is would it be feasible in any way to sort of think of doing the full code and then produce a good enough error model so that's at the catalog space you could add those sort of additional uncertainties to homogenize your catalog at whatever level you want to do that?
I think so, yes. But as Dan's on there and Dan's more deeply embedded in the pipelines than me, he might have a response to that. But I don't think in principle that would be a problem. I'm not sure if it's part of our current processing pipelines.
Okay.
Dan, do you want to throw something in?
Well, I was going to say that the image we do detection on doesn't necessarily have to be the same as the coads we do measurement on. And the simplest example is we could do detection on a multiband image, and that has been tested but not fully implemented, and the impact of that hasn't really been measured yet, but it is a possibility.
Dan, could I add something just quickly to that? If we were to do this though consistently across the entire wide fast deep for data release, that would involve producing 2 coads essentially for every position on the sky, right? To do detection on the deepest and then measurement on the uniform.
Yeah, but I mean, we are already making template coads for DP2. We have also added the pretty coads that we're making images out of. So, I mean, yeah, there is a storage question. If this is the thing we do detection on is something we persist as a product separately from the other coads, but I don't think it's out of the question.
So technically it's not out of the question, but there is a non-zero question of storage cost plus processing time plus etc. The short of it is I can't tell you we could do that right now because it's got budget involved and I'd have to go back and talk to other people as well. But it's
Yeah.
good Dan, that the scientific and technical side doesn't necessarily pose any problems.
And my understanding from previous questions about this was that it was, it probably was out of scope, especially once you included all the catalogs that you would generate from that, as well as the COAD itself. But yeah, I mean, those are really good questions. Like,
But there's also going to be provenance questions as well, and keeping track of all this and what was done on what. So there's all sorts of, you know, data wrangling that has to go in as well. Yeah. Like, it's not just a flick the switch thing. There is work involved, but it's not, it's not, what's the word? Well, we would know how to do it. Like, yeah.
But this does raise the point that somebody else could do it too.
Indeed. But then that also raises the point of, you know, how do we define our data releases as our sort of flagship product? That's, yeah, sorry, we're interrupting Rachel.
You can't interrupt someone who hasn't started talking. So it could be that I missed something, but the way this slide and some of the discussion was framed, it seems like there may be a lack of awareness that there's been a lot of work on DESC in, you know, defining metrics of sufficient uniformity in COADs, and quite a few people, you know, Boris Leistat, Renee Loschek, me, a few others, put a lot of time and effort into getting metrics into MAF, so that they could be, you know, run on the simulations and used to assess them. They cover a subset of the questions one cares about with uniformity. So if there's a strategy that, for example, the metrics currently assume that if, you know, RI and Z-band are uniformish, then the others are. So if there's a simulation for which that assumption is false, they won't catch that. But, you know, a lot of work went into that, and I wanted to advocate for those being included by default and used at least in part to address this. And I also want to say that I recognize that, you know, there are other science cases besides the cosmology ones in DESC for which uniformity matters, and it could be that, for example, for galaxies, maybe the criteria are a bit different, but I do think that having some metrics is better than having no metrics. So I wanted to flag that, and I'll put a link in the Slack channel for this workshop as well to the paper.
Yeah, thank you, Rachel. I mean, you have a very good point, and I will apologize because we did not run these metrics on the current set of simulations. We had missed including this in the automatic processing, and it turns out when we went back to look at it, we actually, there's a NumPy upgrade related issue with running it. So we will look at that. We will work with you guys to make sure we're fixing it in a way that is consistent with your outputs. I think what I'm missing, and maybe this is already in the metric and I'm just missing it, is I thought that the metrics indicated which simulations were better than others, and not necessarily gave the guidance that would be if data management was setting out to make a uniform COAD, what is their specific goal? And maybe I just missed it, and that's like on my part for not understanding what the metric is telling me. But I didn't know if there was a number on like this is the uniformity requirement at the end.
So we might want to talk offline about that. I think the short answer is that for one of the metrics, there is essentially a criterion one can apply, and you know, we used it that way in the paper. But I do want to say that, you know, the reason that people have found it kind of slippery to, you know, is this uniform enough? It's because the answer is that when it's not uniform, one has to try to mitigate that with, you know, like how you do the analysis. So, you know, in principle, if it's really non-uniform, but maybe, you know, people spend like years putting together new analysis methods, technically, yes, maybe they could do cosmology, but like, I'm not sure that's what we should be aiming for. So the metrics generally are about, you know, with existing analysis methods, you know, which still take quite a while, lots of work and validation to apply to, you know, a large imaging survey. You know, is this uniform enough? And we can talk details offline maybe, but I wanted to just share the basic thought process behind those metrics.
Sarah?
Yeah, I think I second everything Rachel just said. Just one part of it, which, and I'm really glad to hear from Leanne and Dan that possibilities are not really off the table. It's not exactly the message that we sort of internalized a while ago, and so I think that's a very positive development. I think part of it was this philosophical idea, right? If you have quote unquote good visits in some part of the sky in time for a data release, are you going to deliberately not include them in a coad? And I think there was at least a philosophical bent, at least coming from some portions of the community that said no, you would have to include them in the data release. And so then we'd be talking about two separate coads, a uniform one and a full one. But I think from Desk, I think also Galaxies, as I recall, had this as their highest priority scientifically, is that for the coads and the catalogs that are made from those coads to be as uniform as possible. And of course, those first two questions, or what does actually mean? What does uniformity mean? I think that's totally a valid question. But if it is possible to do something like that, where we know that those visits, even if they're there, they've been sitting on disk for a few months, and now is the time for the new data release, and they're going to be treated just as single visits, and they will show up in the coad in the next data release or in the final data release. I think that would be a huge scientific win if we could have some sort of definition of what a uniform coad and catalog means. That's up to the scientific community. But as the main product of a data release is something closer to uniform, I think that would be a huge scientific win. So I'm all in support of trying to make that technically feasible and have the science drive the technical and budgetary requirements.
Yeah, and I know Desk did do this analysis of like how much depth you would lose if you were just correcting for rolling cadence all the time. And it was a significant amount of depth. So it is also possible that what we end up looking at is some kind of hybrid where we do decide, okay, these will be uniform data releases, these may not, just based on the rolling cadence. But then there is this aspect of like, we will have non-uniformity from the TOs, from the special surveys, from other things. Like if we include those stripes that Eric showed earlier, right, that were the engineering data, that is very non-uniform. So what do we do with all of this, and when do we want to ensure we have uniform data releases? So I think these are all really good questions, and there's things we can do at survey strategy to make it a good place to start from. But I do think that we can't make it all uniform from survey strategy at the end of the day.
Yeah, I agree. And I was focusing specifically on the uniform checkpoints that are, in either 14710 or 12510, whatever it ends up being, those four checkpoints where we think it's going to be roughly uniform.
Yeah, I think that's a great approach. Leanne?
Yeah, so I put my hand up to say something, and I'm going to respond though to a few of the points that came up. So, Sarah, yes, you're right. In the past, there was sort of more of I wouldn't say it was a message, but it was maybe a bit of a reluctance for us to pivot our strategy to make uniform coads during the construction period. We had the DM science team had a lot of discussions with Rachel and other people on the desk about this. At the time, though, it wasn't so much that we'd rejected the idea, but just that there were other avenues to explore with the survey, and with trying to work this into the survey and not having to make duplicate sets of data products and not having to make two sets of data products. So we wanted to explore all those avenues first before we actually got to the point of doing work, which would have to go into our system to make these extra data products, to curate them, to have provenance, to serve them, etc., and to pay it is a non-zero cost increase to serve up an extra set of coads and do this work. So it wasn't off the table. It's just we wanted to explore all the other easier options first about getting this into the baseline survey cadence. So that's more what that was about. Let's see. What did you You said it would be a scientific win if we could have something like this, but doesn't that really depend on what science people are doing? Because uniform coads does sacrifice depth. And my recollection from, I forget who did the paper, someone on the desk, was it something like 10% over 10 years? Was it? Or maybe it was a bit less than that, on that sort of order. I can't remember. But I mean, you do sacrifice depth, and it is like not including data. So I guess it doesn't depend on what science people are trying to do as to whether it's a scientific gain or not.
Yeah, for sure. I mean, I was sort of maybe responding maybe too eagerly to the idea that there would be two sets. One would be a full and one would be a uniform. And so
Okay, all right.
you wouldn't have, it wouldn't be such a trade-off. I think, for a lot of time domain, that's going to be a lot of single visit science anyway.
Yeah.
We have this separate issue about nightly coads or monthly coads, and there are all these other time scales you could consider for other science cases. So I didn't want to open that discussion, but yeah. Yeah, I fully agree. Yeah, that different science cases will have different requirements. But for Desk and Galaxy, certainly having catalogs as uniform as possible across the sky is a big scientific.
So if we could sum up the two sets of data products, the depth optimized coad and the uniform optimized coad together, yes, that would be a science gain for everyone. I guess I should probably go back and try to cost that now, given that we've gotten to this point. Cost in terms of actual dollars and cost in terms of people, time, effort, all the rest of it. Okay, so what I did put my hand up to ask about, unless Rachel, you want to say something about what I just mentioned, because I have a different question.
It is kind of about what you just mentioned,
Okay,
about kind of the costs and the trade-offs in these different things you were just talking about. So, it could be this isn't quite what you meant, but like when we see some of the depth maps where, for example, the TO observations are included together with everything else, and leading to some splotchiness, at year 10, I had thought that could actually be more effort than a typical coad, because like some of the exposures might have different exposure times. Like it might actually be harder to throw the TOOs in than it is to like exclude them. And so it's felt like the cost trade-off isn't just that the uniform coad is, maybe extra effort, but it could be I'm not totally.
Yeah.
Lynn wants to say something.
Yeah, sorry. A little hard to find all the things and not hit my slides. Sorry. Yes, and then there's also the question that like the TO observations may be at higher air mass and they could be under like non-optimal conditions because the timing is the constraint. There will be visits that are not included in the coads because they don't meet quality constraints. So we're already going to be not including some visits into the coads. And so this is maybe like adding an extra level of intentionally excluding visits, which could otherwise have been included, I think is one way to look at it. I'm going to say we should move along to DESI, but we do have extra discussion time after DESI to cover any questions that have come up throughout all of this area. And I also do think this is very good preparation for when we talk about the DESI stuff, because that does also introduce some non-uniformity. But I'm going to so if you have something to wrap up here real quickly, Anne, you go for it.
Very, very quickly, but we can come back to this in discussion. You've got a good starting set of questions there. A couple of others that I'd throw into it are, and very importantly, how do we select which images to not include in the coad? And there's a whole lot of criteria. We already have quality cuts on images to include in coads, like seeing, for example. But, does, for example, the time distribution of images throughout a coad have any impact on the science people want to do? So that's also a really important one that I think data management cannot decide. And we need some sort of algorithm, we need some sort of selection process agreed by the community across all sciences as to how optimally to decide, what are the criteria that you want to cut on and how do you combine those criteria to satisfy all the different sciences. That's just another important question I want to throw in there.
Yeah, I didn't write that, but that is definitely a good one. How do you pick the visits? Okay. So I'm going to give a really brief overview on what we did for the DESI simulations and how that contrasts to how we would be acquiring visits otherwise. And then I'm going to hand this over to David, who will tell you all about the great synergies that come out of what could be enabled by this change in the survey strategy. So the basic idea in the request is to take this about 5,000 square degree area that is shown here in the yellow and purple areas and sort of accelerate the coverage of that area to get to a depth of 30 to 40 visits in each of UGRIZY by the end of year 4. And the initial sort of question was, could we get to the yellow portion of that footprint by the end of year 2? On the left, what I have is the median number of visits over the sky in the baseline survey. So this is a median and sort of just without any influence. And as you've seen before, rolling cadence does start to influence things after when you get to year 2. But this is sort of median number of visits that we would have over the sky, and you can see in RIZY in the redder bands, we would get to that or close to that depth at the end of year 3. And then U and G are where we have the problem with this goal, because at year 3, we're still very far back at like 10 and 16 visits. Note that our template tier has already accelerated U and G in year 1 to get to the number of visits we need for the templates. And we don't actually reach 30 visits in these bands until year 6 or year 8, if we go with a natural cadence. So that's the primary problem. What you see if you look at like R band is at year 4. So after the year 4 would be the end of the request. Can you cover this footprint to your to this number of visits by year 4? At year 4 in G band, the DESI footprint is very obvious because it's ahead of the rest of the sky. And at year 4 in R band, it's not really very obvious, which just matches what we see from the number of visits per year. The other thing to consider with this is that within the DESI footprint, so this is the number of the night and the number of visits we've acquired up to that night. And so in year 1, we really, because we have this template here, because we're pushing hard to get all the visits for the template, there isn't really that much of a change whether you're in the DESI footprint or outside the DESI footprint. We're doing the same thing in year 1. But after year 1, if in the DESI simulations, we sort of switch over to like, okay, let's try and get the visits for this footprint, you can see that it accelerates. And so we get up to, this is a part in the year 2 footprint, so the yellow area. So you can see we get up to, maybe not. Okay, sorry, it's not Y band. So we get a lot of visits in UGRIZ because of being in the DESI footprint. But then after you get that number of visits, because now you're very far ahead in this part of the sky, you get very few visits for a very long time. And then eventually the rest of the sky catches up to you. And so you say, so the scheduler says, okay, great. Now we're balanced in the footprint, and we should start taking visits here again. And so you see this acceleration and then a wait until you take more visits. And that's not as strong in the redder bands because those are more on par with the rest of the sky. And then outside of the DESI footprint, so this is a much lower declination that's outside of that footprint, you see that you get a little bit of suppression in that period where the scheduler is concentrating on DESI, and then you start recovering visits after that. And of course, we can look at our metrics. The metrics here, so this is DESI, and we have 2 simulations for the DESI footprint. sorry, we have two simulations to date for the DESI footprint. DESI yearly does that yellow band and blue band completing by year 2 and year 4. And the DESI 3040 actually tries to complete the whole thing by year 2, which I'm sure DESI love, but this does have more of an impact on when you'll see that delay in the footprint. And it's kind of a much stronger effect than we actually intended. So the DESI yearly completes the request by year 2 and year 4 on the relevant parts of that footprint. And it's not clear to me that our current metrics, especially when we evaluate at the end of year 10, that they really capture any potential benefits or the full impact for this. So I think you need, we take this with a grain of salt. There certainly are some metrics which don't seem to be impacted by the end of year 10, which, as you would expect, the coadded depth, if you have static science that only cares about coadded depth, at the end of year 10, the coadded depths are very similar. You didn't gain or lose by having this reshuffling of the observation cadence. And for some time domain, this will be an impact, and it's not obvious that when we look at the impact at the end of year 10 that we've captured this properly or not. And then I was going to say, we do have one simulation that we have not made yet, but that we will look at, which it's not clear it will make a huge difference, but the idea is, instead of covering the whole footprint by year 4, instead we split it up into smaller chunks and let the last chunk sort of hang off the end, so it's at the end of year 5. And so this is not necessarily the order you would do this, but I made a little plot to give the idea. So the different colors on the right are like doing about 1,000 square degrees at the end of year 2, another by the end of year 3, and so then you end up with the final 1,000 square degrees being completed at the end of year 5. And it's worth noting, like, this, one thing that would happen here is that after year 3, and maybe even during year 3, you wouldn't be accelerating any of the redder bands. So the redder band cadence will only be disturbed in 2 of these bands, but the bluer visits, like U and G, would still be disturbed in all of the band passes. And it might not be quite as strong of an effect, but it would still be there. And you would still, if you completed to 30 visits here at year 5, you would still be sort of waiting until about year 7 or 8 until you started picking up more visits in this area, unless we do something else again, like add more visits in U and G to this part of the sky, which is yet another variation on the survey strategy. And it's not super clear, given that we've lost 10% since we've updated our forecasts to be slightly fewer visits overall, what exactly the impact of that is. So now I'm going to turn it over to David to tell you about all of the good things that come out of this. Sorry, Kathy, you have a quick question?
Yeah, my question, Lynn, is how do you see this DESI strategy with combined with rolling cadence?
Yeah, so the original request was actually quite smart, because it doesn't quite line up. Now we've changed the start of the survey, but in the original version of the survey strategy, where we had started the simulation on November, this year 2 and year 4 did align with the rolling cadence, so it was kind of like building on the rolling cadence. When we changed the start of the survey, we changed which part, like the part of the sky, and so there's some changes about whether we're in a up deck band or a down deck band, and so it doesn't quite align anymore, but that's something we could reinstate. And certainly when you look at something like this, we could arrange these to be more smartly aligned with the rolling cadence. All right, I do want to make sure that David gets gets to tell you about the good aspects here. So I'm actually going to cut off questions and we can come back and discuss this more afterwards. David, is that okay? Are you?
Yeah, no, that's good. Yeah. If I could share also.
Yes, sorry.
And
Stop.
yeah, let me start with Lynn. It's been wonderful working with this SCOC group, very responsive, and we are trying to, approach this in a way that we're making minimal impact on Rubin observing. Okay. This is my one slide about what is DESI. Hopefully you've heard of DESI before. It's really the most wonderful multi-object spectrograph on the planet right now. Over the past 5 years, it's mapped 47 million galaxies, 20 million stars. This is a fully 100% DOE funded operation. So we're making use of the Noir Lab telescope at Kitt Peak. And then here just the basic stats on this, where it's 5,000 robotic fibers, broad wavelength range, and the data quality is just wonderful. Partly because every observation we get simultaneously 100 standard stars, 600 skies, so we can really produce excellent Poisson limited spectra. Okay, these are just representative spectra, and these are truly representative of what the DESI main survey has been doing, because we do these dynamic exposures where we adjust the open shutter time according to seeing, sky brightness, transparency. And I do want to know, you're talking about uniformity. We're now operating DECCAM in exactly this mode. It's not too late for Rubin. And here's some quotes here. Like, what do people say about dynamic exposures? All good things. From my perspective, one of the best things is we actually get a faster survey, because on good nights, we collect about twice as much data as you might expect. So we really do a lot of catching up on the prime nights. So, you're talking about, you want to get 10% back, you could easily get 10% back. Okay, starting, actually, I think it's tonight, DESI begins mapping further south. So we've expanded the DESI Run 1 footprint. This is the expanded footprint for DESI that we'll be doing over the next couple years. And I just want to note this because this new area fully overlaps the Rubin footprint. Okay. What we're interested in enabling here, though, is what we're calling DESI Run 2. So this will be the next phase of the DESI project starting in January 2029. Most of the dark time is focused on a cosmology experiment at redshifts 2 to 3.5 over this 5,000 square degree equatorial footprint that Lynn was just showing you. And we chose this footprint not because it's necessarily our best footprint. It's a little too far south for us, but again, we're trying to minimize our impact on Rubin, so we're fitting this in on the northernmost good sky that Rubin was already planning on observing. Okay, so we have a proposed data exchange between DESI and Rubin. So this is following the policies of both collaborations, where what we're asking from Rubin is this early imaging when necessary over this equatorial footprint. And that's what we'll be using for target selection for DESI Run 2. So, obviously we need this before DESI Run 2, just so we can select the targets. And then in return on this data exchange, what we've put on the table is what we call 250 effective dark hours. What that corresponds to is 4.5 months of DESI time. And what can be done with 4.5 months of DESI time? Well, if you're talking about the kind of data we've been collecting typically for the last 5 years. That would be 4 million spectra. Or one can do deeper observations. So, hundreds of thousands of spectra deeper, or some combination of all of these. Another point here is that the data are fully reduced. Typically, by the time I'm having coffee in the morning, and I get up early, so these data they're spooled over to NERSC during the night, and we say typically available within 12 hours. If you're impatient, they're actually available faster than that. Okay, these observations would be coordinated between the two projects so that we make best use of this time. Examples of what could be done that this DESI Rubin working group has been looking at so far are primarily based on observations in the two deep drilling fields that are available to both telescopes. So we could go quite deep in these deep drilling fields for photo Z catalogs in these footprints. And also, we could be observing transients within a day of discovery. And in practice, we can do these in such a way that we do observations where you're doing both simultaneously. So you're observing these deep fields, you're picking up new transients, and then you accumulate signal to noise on fainter objects at the same time. DESI has already measured about 250,000 redshifts in these two deep drilling fields already. These footprints, they're essentially the same size as the Rubin footprints. The field of view of both instruments is about the same. This just shows you the density of targets that we've already published and just, you can see the scale here, 50 arc seconds. So very high density of targets that we've already observed. So it's kind of a down payment of what's available in these deep drilling fields. We've also demonstrated that we can go quite a bit deeper. So we've taken data up to about 5 hours and demonstrated that we can get Poisson level spectroscopy. So these are objects where we've observed 3 or 4 hours, 24th, 25th magnitude spectra. So this is all published. We also have a pretty good understanding of redshift success rate as a function of integration time. So this is also something that was just published a couple months back. So this is looking at that success rate versus exposure time. It's actually very dependent on the magnitude and colors of objects. So there are parts of color space where we're already doing this right now. We're observing, for example, luminous red galaxies at redshift of 1 in 15 minutes, just because it's a color space where we know we can very quickly get a successful redshift. Okay, timeline. So we really need the first bit of the Rubin imaging available prior to the start of this DESI Run 2 in January 2029. And we could, it'd be great if we could have all of this prior to 2029, but we're willing to work with Rubin and space this out over a few years just so that the Rubin imaging is still prior to each footprint that we're observing with DESI. And then for this data trade, so the DESI spectroscopy, this could be provided early, and or it could be cadenced throughout the DESI Run 2 going through 2034. So in other words, what we're imagining is early in DESI Run 2, we would do some deep observations in these deep drilling fields, and then over the course of maybe the next 4 or 5 years, do transient follow-up in those fields. Okay, and then let me just end with DESI has no plans to coordinate with any other survey, so it really is just the Rubin that we're trying to coordinate with this on this. Okay, so that's actually all I had to show. And I should note there are some other DESI folks on as well. We tried to not overwhelm your call, but who could answer questions here?
All right. Thank you, David. That's a great demonstration of what we gain from doing this. Yeah, let's go with questions now. Dan?
When you say you don't have plans to coordinate with other surveys, do you mean imaging surveys or also upcoming spectroscopics? I'm thinking of Subaru PFS is definitely going to target deep fields. Foremost, I guess, is not really overlapping, but and I don't think they've asked for anything specific, but could you not also make the argument, well, we should also prioritize covering like the waves, foremost fields in a similar fashion?
Sorry, that DESI should be coordinating with waves or what?
No. So for the first part, are you coordinating at all with Subaru PFS in the deep drilling fields, for example?
Yeah, so we don't have any coordination. So the only other coordination we have is we are obtaining other imaging that we need for DESI Run 2 from several different telescopes. We're running those imaging surveys within DESI. These are medium band imaging surveys. So that is our other coordination. That's just internal. As for other spectroscopic projects, we're really far ahead on DESI, and it's kind of the question gets turned on its head of, these other projects shouldn't repeat what DESI has already done.
Rachel?
Yeah, I have a comment and a question, if that's okay. So the comment is more on the earlier part of the presentation. There was a statement that the metrics, for impact of these strategies on the science may not capture, the full impact. They may not be designed for that. I want to actually strengthen that to say that several of the desk metrics definitely do not capture the impact of this change in strategy because they make assumptions about the coverage in each band tracking each other in a way that these simulations violate. So I think it's a stronger statement that, we'll likely need to update the metrics. But then to ask my actual question, one other timeline question that I wanted to understand is, when would a decision have to be made about doing this? Like, at what point would the Rubin strategy need to start to deviate from what it would otherwise be? Because that feels like a pretty important and relevant factor to understand.
Yeah, that is a great question. I don't actually have a super good answer for you, except for the fact that I would say when we did run these simulations with the DESI survey, like the DESI 3040 and the DESI yearly, there was no change inside of year one because the template tier was put in at a higher priority. I'm assuming that's right. Is that right, Peter?
Yep, that's right.
Yeah. So the templates being a higher priority meant that the templates were trying to get their visits. And because the templates take up most of year one, it just basically means there's no actual impact. So yes, we should decide as soon as possible. In practice, if our priority is actually first getting templates, which I think it should be, but that's my opinion, of course. But then we have some time in practice. We should definitely decide before. I mean, ideally, we decide as soon as possible because it makes a difference for funding for various things, right? But in practice, if we had a strategy in place, like a decision in place 6 months from now, I think that would it would not really impact what we're actually doing on Sky.
Yeah, and to be clear, it's not like I wanted to push to wait until the latest possible moment. It was more trying to understand, is this like a right now decision, or
Yeah,
we should do
yeah.
this within a couple of months and the time will fly. So yeah, thank you for clarifying.
Yeah, I mean, let me just say from the DESI side, though, we're eager to get to a decision point quickly, even if this isn't perturbing Rubin observations for another year. And that's just, you can imagine this could blow up the DESI run to planning.
Yeah, definitely. That's good. Roberto?
Yeah, so we discussed this a little bit on the impact on the AGN science collaboration in the latest telecon, and there were a couple of questions that that I think were very interesting. It came up. So one was, is the DESI2 footprint fixed? And if so, do you know how much does it overlap with Eurosita, or at least the German part of Eurosita?
Oh, that's a good question. I don't have that right in front of me, but maybe one of my collaborators can figure this out quickly. But I mean, you can look at it. It must be a fair amount of overlap because we're overlapping LSST, which has a fair amount of overlap.
Mhm.
So sorry, I don't know that offhand.
That's fine. But the other question was, so right, currently the offer, right, is the exchange to 250 dark time hours. One of the questions was, would it be instead, or with some partition, access all the DESI spectra, taking over the LSST footprint?
So all of the DESI spectra, that they are made public on some time scale. And in fact, the DESI DR1 release, which goes back a year now, most of that is actually over the Rubin footprint, in fact, just because we started, or it must be more than half because we started kind of equatorial with DESI. So we've not discussed that. The DESI director is on. Maybe he would like to respond to that. Michael?
I'm sorry, what was the question?
Oh,
Yeah, sorry.
do you want to just repeat your question?
Sure. So the question that came up was, could there be access to the private DESI data, DESI2 data, on the regions that overlap the LSST footprint?
Well, the 250 hours that we're talking about, I think the answer is yes, because you would be defining what those are.
Oh, right, but not, okay. Okay, so I think the question was, instead of the 250 hours, access to all the spectra. But I mean, I see what you mean, right?
Yeah.
So we could coordinate to make sure that it's regions of
So no,
interest.
this is not an offer to open up the all of the proprietary DESI data. I mean, that would be, it's possible for, you as an individual to come in to DESI as an external collaborator with a particular scientific project to work with one of our other collaborators within DESI, to work with us on a topic where then you would have access to some of that information. So that it's technically possible. A broader, if you're asking a question, well, what about a collaboration between DESI and eRosita? That's probably out of context for this meeting. But
yeah, absolutely.
Yeah. So I think that's, would be a different format than what we're talking about here.
Okay. Thank you.
Rob?
Yeah, David, I just wanted to understand a little bit better the DESI run to needs. And maybe this is probably in some document, and I apologize if I have not read the appropriate document. But the example spectra you showed, like even the long exposure ones, were getting down to, 23rd, 24th magnitude. And I guess I understand that the DESI run 2 is targeting somewhat higher redshift, so maybe slightly fainter is the goal. But that was a surprising number a little bit to me because if you're requesting 4-year-ish Rubin depth, that seems a lot deeper. So, even in one visit, you're getting to close to 24th magnitude in U, 24.5 in G. So it feels like in a few visits, I know maybe you need signal noise of 10 or 50 in the images, so maybe you just need very high fidelity photometry. But it seems like in 4 years of Rubin, you get down to like 26th magnitude. And so is it possible that you can do the target selection with less data from Rubin?
Yeah, we started with a request that was even deeper, and then dialed that back after some studies. The reason is, these are the high redshift galaxies for which we can most efficiently and quickly get a redshift. So they're not typical redshift 3 galaxies. They're the ones that we can get a redshift of. So primarily you should think of these as the U dropout galaxies, where if you want an efficient selection of it's just the brightest U dropout galaxies, you need about these 30 visit depths. The other objects that we're looking at, it's these Lyman alpha emitters where their broadband photometry is really quite faint because they're objects where we've picked them up as a 25th magnitude object in medium band imaging, and then the broadband depth is deeper than that, but we still want the broadband color to distinguish those from interlopers. So we've looked pretty carefully at these depth requirements.
Maybe to complement that, we have run target selection with random forest, assuming different depths of LSST. And for 4-year depths, which is equivalent to what we're discussing here, we get a purity of only 55%. So we really need that depth to get an efficient survey afterwards.
Thanks.
John?
Oh, sorry, I didn't realize my camera was off. So I guess so my science case, it doesn't make any difference in the long run, when you move the filters around, and particularly the blue filters. But I do want to ask, because I've spent a lot of time lately hearing about Roman. It seems like this preferentially moves U and G observations out of Roman overlap in the upcoming years. And since we now believe it will really launch in August, it seems like this is a very high impact on the American astronomical community to lose that potential science case where presumably Roman can't observe U and G. So there's really adding something to that. How will the SCOC, I don't think it's a question for David, address, those sorts of concerns? What the views of other communities that aren't necessarily LSST centric do? So it's a question to raise a big issue, I guess.
So I don't think this is a question for me to answer, as I'm a ex officio member of the SCOC. However, Fed is not actually with us today, unfortunately, due to personal
I'm in Uber, so there may be too much background noise. I apologize.
There we go.
But as Lynn said, we want SCOC to focus on scientific impact of this cadence change. And other aspects of this proposal will be considered elsewhere. There are, of course, many other aspects to it. But SCOC is in the best position to assess what would be impacts on LSSD science cases if we followed the strategy that we already simulated in response to this proposal. That is the main goal for this committee. Those other aspects that are valid and that we need to consider, they will be addressed elsewhere.
Yeah. So overlap with external surveys is out of bounds, but a purely LSST consideration of the impact
Right.
that's very helpful for us to understand. Thank you so much.
Okay. Sorry for the noise.
I think it is certainly a goal in general of the SCLC to consider as many aspects as possible of survey strategy changes as they come up. There is always, of course, the limitation that um, our knowledge within the project and our knowledge from coming from the science collaborations will be imperfect. And so if this comes up through the science collaborations that they say, oh, one of the things that I'm now concerned about is like how LSST survey coverage is going to impact my other science. It's true, that's a little bit it's a bit of a question that's like out of bounds for what the LSST is because the priority of the SCOC has to remain the LSST science, but it certainly is something that they can think about. Nobody's going to say they couldn't consider something. But yeah, there are always unfortunately things that we're going to miss, of course. But at the end of the day, we are here to try to make the best LSST. And let's see. We do have some more time here for questions. We can talk about DESI, and we can talk about other questions from other parts of the session. I do want to make sure if we have things we want to circle back to from the rest of the workshop that we cover those as well. But so Dan.
Yeah, sorry, I had a lingering question from before, and I missed the discussion about the DDFs earlier, but looked at the slides. Do you have a lot of metrics for specifically optimizing the radial dithering or translational dithers in the DDFs? Is it basically trading off the area that gets full coverage versus the larger area that might get less coverage on the outskirts? And does that one failed detector that's very near the edge of the focal plane, but not quite, does that change things at all, or?
Okay, so this is a good question that touches along a lot of on a particular math aspect as well. With math, what we do is we do imprint the camera footprint when we're calculating our metrics. We don't necessarily have the resolution to really say this is we don't usually run our metrics at super high resolution. So we represent the chip gap statistically, but not necessarily exactly, for example. That said, we should take our camera footprint and take out because we do have the chip gaps in our camera footprint. We haven't taken out the missing detector, and we should do that, and that's a very good point. So I don't know if the missing detector makes a difference or not. The metrics we have for the deep drilling fields and the dithering really do just, as you say, look at the trades between as you get wider, bigger dithers, you decrease the cadence. So we do have things that are looking at like essentially what is the cadence within the deep drilling fields, and you do decrease the co-edit depth because you're spreading that over more area. I don't know specifically we look at like what happens with the roll off, but as you towards the edges of the dither, but we definitely that is the primary driver for having smaller dithers is you get a better cadence and you get deeper depths. Rob.
Yeah, just to follow up on that. So yeah, it's true that the metrics don't always capture that for the DDFs, but this is something we put in the DDF task force of the SCOC we posed to the science collaborations. And basically, you can imagine you have this umbra of the DDF and then you have this penumbra, which gets bigger the more you dither. And you could imagine some science cases would like, basically you're making your effective area of a deep drilling field just bigger. Um, but it turns out in terms of like external synergies for the DDFs and like, space-based imaging and stuff, that the Rubin footprint is already big, right, compared to the size of these fields. And so increasing that area was not generally a science win across the board for the science collaborations. And so from the science collaborations point of view, keeping that as small as possible, like maybe just dithering over chip gaps, that would be the ideal. And then that would improve the cadence, just as Lynn said, and get the highest go-added depth. So basically, the dithering we would want to do with EDFs is as little as possible that DM says is okay.
And it does seem like we've moved on to other questions, so I'm gonna make sure we thank all of the DESI people for joining us. Your course, like, please stay on so that in case we come back to more DESI questions. But thank you for your presentation and joining us. Neil?
Yeah, sorry, I just did want to ask one other just point of clarification, just to be sure I didn't miss something along the way. So if the DESI plan were implemented, what would you anticipate the effects upon the deep drilling fields, if anything material to be? I presume we would still maintain truly excellent time domain coverage in any of the deep drilling fields that are also in that footprint. That's obviously very important and is key to the nature of the deep drilling field, in terms of the U and G bands. But are there other effects you could anticipate there that we should be thinking about?
I
So
haven't.
let me jump in for a second. I mean, I don't see why this would affect Rubin at all, but we do have the opportunity on the DESI side. We don't have any other cadencing requirements or anything like that. So if the request for this data exchange from DESI said, hey, we really want to do the DESI follow-up on the following days, or just more of a triggered response, we could do that. So that I think we'd certainly see that on the DESI side.
Thanks. Yes, I'm mostly interested in the Rubin side here. So Lynn, do you have any insights there? I mean,
So it's true. I haven't specifically looked to see in the DESI sims, did we change the deep drilling coverage? However, I would guess we did not, and so Rob is shaking his head, because of the fact that the deep drilling fields are programmed separately and they're in a higher tier. So they should continue as previously planned. And we didn't like decrease the DDF coverage because we were getting this other coverage as well. So
okay.
Yeah, I was going to say the same thing, that the DDFs are not affected. It's really the WFD visits in that northern part of the sky that get shifted.
Very good. I just wanted to be sure there wasn't some second order effect that I wasn't appreciating, but thank you. Okay.
no, in fact, it's usually the other way around, that the DDFs affect the coverage of the rest of the sky because they are in this higher priority tier. And this was, for example, one of the reasons we had to move the ultra deep season of EDFS out of year one, because we were already a little stretched thin in that part of the sky. And with like assuming a higher fault rate and lower efficiency at the start of the survey, it made things a little bit too tight. So yeah, the deep drilling fields are very strongly defined, I guess, is one way to put it. All right. Do we have other questions? We have about 10 more minutes. Yeah, Rachel.
Yeah, so this is a question for Rubin leadership. So looking at who's on the call, maybe Phil or Jelko. So for the DESI observing time that would come out of this exchange, like, does Rubin leadership have an idea for a model for how to allocate that to maximize the benefit to the Rubin community?
I would say not yet, but we have have already done some thinking about other in-kind contributions of telescope time and so on. So we would look at what we've done there with contributions from Subaru and other places, and think about whether we could treat this the DESI time or the DESI data in a similar way. I mean, we're trying to be even-handed in our support of the LSST science community, and NWILAB has open skies policies that we're trying to observe as well. So we would try and make sure that the benefits of any data exchange with DESI were shared around. It may well be that some parts of the LSST science community would benefit more from this than others, and we would try and take that into account as well. But I mean, there would be something significant to work out here in terms of how best to use these data. I mean, I suppose there's some hope that there could be simple ways, and I think David was highlighting these in his slides, simple ways for using DESI spectra kind of synoptically, similar to the LSST survey itself. So looking for applications that already serve multiple science cases, and PhotoZ training is one of those, for example.
Yeah, so I'm just reiterating what David showed, but with just a one-slide summary of topics that we've discussed for collaboration between DESI, Spectra, and LSST, and in the deep drilling fields in particular, we can really contribute to the LSST science, the Rubin science, by providing the spectra of live transients or a supernovae host. And for the weak lensing science, we can also significantly support that science by providing the very deep spectra for PhotoZ calibration. We've tested up to a few hours, but we've shown that with the instrumentation upgrade that we're planning for this second phase of DESI, we could actually stack up to 80 hours of spectra. And so that would really provide very deep spectra for calibration of PhotoZs. And so this is an example of what we've been discussing so far, but of course, this is not set in stone, and we can definitely continue to identify what would be the best outcome of this data exchange.
Thanks, Natalie.
Well, I think we've covered a lot, and we've had a lot to think about. I don't see any more questions or hands coming up. So I'm going to say thank you all very much for coming and sharing and talking with us today. And all of you community members and all of the SCOC members, thank you as well. It's been a lot to go through and to talk about, and I hope we all have some good ideas of how the survey will start, what we're doing in terms of the strategy, and where we might be going for the next year and two, as well as over the 10 years of the survey. You know what? I think we can be done. We can have a few minutes back out of your day. And thank you all for coming. We do have Monday coming up, and I'm hoping that Fed will be back to help us coordinate for that. But otherwise, we'll be reaching out to the science collaborations to organize feedback. Monday is a little bit more for feedback from you in the science collaborations to the SCOC. So thanks very much. We'll talk to you on Monday.
Thanks, Lynn.